In the next half hour or so, we would like to introduce you to GibbsCAM. GibbsCAM is designed for shops of all sizes and skill levels. With GibbsCAM's wide range of software options and easy-to-use interface, you can run any CNC chip-making machine in your shop, from 3-axis mill to complex multi-spindle 5-axis plus machines. GibbsCAM can help you be competitive and can grow as you add machines with more complexity. GibbsCAM was designed by machinists for machinists and has enough simplicity for novice users and enough power for the most demanding applications. The GibbsCAM workflow is 6 steps. Step number 1, document control. Select your machine type, material, basic stock size, units, mill class, and master clearance plane. Step number 2, either draw or import a drawing of your part. Step number 3, create your tools and your tool list. Step number 4, create your machining operations. Your operations live here on the right side of the screen. Your tools live here on the left. Step number 5, simulate your part. See it before you machine it. Step number 6, post your code. The 6 simple steps of the GibbsCAM workflow allow you to work quickly from end to end on your part process. Let's begin this demo by changing part files. We want to show you how we process this part from start to finish. Using GibbsCAM's powerful CAD system, we will turn this 2D drawing into a valuable 3D solid model that can be used during operation simulation to give you confidence before you send the code to the floor. See it before you machine it is a very important part of GibbsCAM. Let's have a quick look at the part drawing. It's 1.25 inches tall. It has a 1-inch step, a 1/4-inch step, 5/8 and 1-inch holes, and now we have a pretty good idea of what the part looks like. We've created a custom toolbar to help us turn this 2D geometry into a solid model. Standard solid modeling tools of extrude, revolve, slice, and blend are built into the GibbsCAM's powerful CAD system. Let's first extrude this outside shape down 1 inch and all the way down -1.25. With a simple click of a button, we took a 2D shape and created a 3D drawing out of it. We now need the intermediate step. Let's flip these 2 arcs over using the reverse arc command, which is Control-T. We want to extrude this upwards of 0, downwards of, well, we forgot. Can we get the dimensions directly off of the previous workpiece? Yes, we can. Pressing the Alt key will allow us to take the dimension from the part and put it in the appropriate data field. After we double-click the geometry, we simply click Do It, and there is the intermediate step of our part. Now, don't forget we have the upper step here. Let's flip these 2 arcs back over using Control-T and extrude it downwards of 1/4 inch, -0.25. We are going to also extrude it upwards just a little bit so that we have a handle to grab a hold of when we go to perform the subtraction operation, which is next. We're going to take this body and subtract this body from it to give us the step using subtraction. Now these 2 pieces need to be added together using union. Solid modeling is very simple inside of GibbsCAM. Let's get all the holes at one time. Upwards of 0.1, downwards of something greater. Let's find all the holes. Click with your Control key. Because GibbsCAM is not only Windows compatible, it is Windows certified. We're going to extrude all of these circles at one time and then subtract them all at one time using the GibbsCAM subtraction. Now we have the counter bores, and the counter bores, we will extrude those as well, upwards of 0 and downwards of minus 0.250, minus 0.160. Yes, every data field in GibbsCAM is a calculator. When we create this extrusion, we can now subtract it, and we will have the counter bores in the top of the part. Turning this part from 2D geometry to 3D geometry is very simple. Now that we've done the bulk of the work, let's hide the 2D geometry and do a little 2.5D blending. Solid models are made up of faces and edges, and GibbsCAM uses those faces and edges to your advantage. Here we have two 1/32 of an inch chamfers on the outside of the part. We will use the blending button and chamfer with a length of 0.03 and do it. Yes, we can do multiple chamfers at one time. This one on the bottom, we're going to double click and chamfer it 30 thousandths. This hole gets a 50,000 chamfer on it, 0.05 and do it. And the tops of these holes get a 5 thousandths edge break on them. We will cut that edge break with a spot drill, 0.005 thousandths. The part is now complete, and now let's show you how to import a solid model. Not only can you create high-quality solid models inside of GibbsCAM, but if someone sends you a solid model, you can bring it into GibbsCAM using the powerful import utility. Simply go to File, Import. Select the type of file that the customer sent you from this extensive list inside of GibbsCAM. In this case, it's a parasolid. Let's select the parasolid and open. Once the model comes in, you'll see that it is part of an assembly that came from outside of GibbsCAM, and it is not aligned to the machine axis because of its place in the assembly. It's a simple matter and only requires a few clicks to align this part to the machine axis. We're going to use face and edge selection again. We'll select this top face, which is central to the part, right-click, align face to CS. Most of the rotation axes have been aligned to the coordinate system of the machine, but we have our third rotation axis that needs a little bit of work. Let's select this horizontal edge and align it to the horizontal axis of the machine, which is X. We click the edge, right-click the edge, align edge to coordinate system horizontal, and now you can see that all of the rotation solutions are done. We now only need to move the Z top of the part down to Z0. We will do that using the Absolute Translate menu. This gives us an opportunity to look at the Absolute Translate menu and to see how simple GibbsCAM menus are. Simple, precise, and to the point. We want to move the model from here down to 0. With a minimum of operator input, we can find this information directly off of the solid model. By double-clicking in the Z from position, press your Alt key down and click the top edge of the part. We want this part to go from Z.25 down to Z0. Simply click on the part and select Do It. Our part is now fully aligned and ready for the next step in GibbsCAM. It's time to start machining this part from scratch. Let's open a part file that has no machining in it, just the part and the vise. No machining, no tools. To begin with, we will go through the GibbsCAM workflow step by step. Document control is already complete. Geometry is already complete. It's now time to go directly to step number 3. Let's create a tool, the face mill. Double-click in an empty tool slot, select face mill. This is a 2-inch face mill. The bottom radius is 0.0156. The lead-in angle of the face mill is 45. The shank is 0.875. The cutting height of the insert, 0.22. The total height of the insert, 0.625. Number of flutes equals 5. Length out of holder, 0.625. Let's change this to a mill holder and carbide insert coated. By the way, this is a Sandvik 245 face mill. It is ready to use. The next step, step 4 in GibbsCAM, is to create the machining operations. Drag the tool into the process list and select roughing. In roughing, we have face milling, boss milling, and pocket milling. Clicking the material button will take us to the material database where we can select an appropriate feed and speed. We simply click Calc RPM and Calc Feed, and we're done. Cut width is 70% of the cutter. 2 times 0.7 equals. We will be machining stock, not a shape, one direction, roll-in entry as per the manufacturer's instructions. Start corner will be X plus, Y minus. That way we don't throw the chips at the operator or the plexiglass door. First cut will be in the X minus direction. The Z start of this toolpath is 0.025, and the Z ending point of this toolpath will be Z0. The XY clearance on either side of the part will be set to 1/2 of an inch. Now we simply click Do It, and we have our facing toolpath. Let's create our next roughing toolpath, and let's make an end mill to go with it. A rough end mill, 1/2 inch in diameter, with a small corner radius that makes the end mill last quite a bit longer. Flute length, 1.5. Total length of the end mill, 3 inches. Number of flutes, 6. Length out of holder, 1.6. Down here, carbide solid. And let's go with a shrink fit holder. This cutter is now ready to use. We will drag it into the process list and select volume mill. Volume mill is the premier roughing operation in the world today. The technology expert allows you to quickly set the feeds and speeds for this high-speed machining process, which will cut your parts twice as fast with 4 times better tool life. All you have to do is select your material, your hardness, your machine taper, your max spindle RPM, your max feed rate, toolpath type is volume mill, tool holder, shrink fit, tool coating is coated. The RPM, the feed rate, the depth of cut, and the width of cut have automatically been calculated by GibbsCAM and volume mill. We only need to select Apply All. Then let's check our XY stock, leave it at +20. Use stock material only to eliminate air cutting. The top of the toolpath is 0 in the Z-axis, and the bottom of the toolpath is -1.280. The part height, remember, is 1/250, and we want to go just below that. Plunge type is do not plunge. Helix would be used if we were machining a pocket. Now, we simply click on the part and do it. The process manager is running, and we will have a toolpath very quickly. We have now roughed out the bottom of the part. We now have an intermediate step here at the 1 inch. In volume mill, it's important to note that we start from the bottom up rather than old school milling from the top down, because in volume mill we can use 2 times the diameter depth rather than the traditional 1/2 of the diameter depth. Let's get the depth of this step, which we may not remember. Let's have it populate this data field automatically with an Alt click, and you can see it's -1. We don't need to change any other parameters other than clicking Do It, and we will have a toolpath on the intermediate step. The next step is the upper step, and again, we may not remember, but let's let GibbsCAM do that for us. Minus 0.25 and do it. The part is now fully roughed out. Let's move forward now, and we have no more tools, but we have some saved processes. A saved process allows you to create a tool and a machining process, along with the feed, speed, depth of cut, and other cutting parameters. Then, once we import that, the tool and the process are ready to use. We'll go to the Feature menu, Hole Manager, Run AFR, and Auto Group. The holes have now been highlighted, and we can click here and here to drill our 5/8 holes. Remember, this hole making process includes automatic functions that will detect the top and bottom of the hole. Let's do the same with the 1-inch drill. Right-click in the process list, load process, and let's grab the 1-inch drill. Open, and again, when you import it, it senses where the top and bottom of the hole are automatically because we are using the automated drilling functions. We now have all 3 holes in the top of the part drilled. Let's finish the outside of the part with an end mill now. We don't have a finishing end mill, and we don't have a finishing process. Let's right-click the process list and select Superflange Contour Finish. In Superflange Contour Finish, the RPM, feed rate, and the tool are all connected together. We only need to turn on the profiler. The profiler automatically extracts geometry for you so that you do not have to do it. The profiler is settable for depth by right-click, and you can automatically set the profiler depth, or you can manually drag it into place. All we have to do is click on the geometry that was highlighted by the profiler and do it. And we now have a finish pass around the outside of the part. We need to finish the intermediate step on the part, and yes, we will use the same process and simply raise the profiler up until we get the intermediate step geometry. We need to change the Z depth of this process. When we double-click it, double-click here, and alt-click this surface, that surface automatically jumps in the Z bottom of the toolpath data field, and all we have to do is click Do It. We will do the same for the 2 bosses on the top of the part. Drag the profiler onto the bosses, click the highlighted boss geometry, double-click here, and alt-click the top of the surface. When we click Do It, you will see we created 2 tool paths at one time, but we have the wrong dimension. Let's fix that by alt-clicking here again. If you make a misclick, you can fix it very quickly and hit the redo button, and your toolpath is now done. We have roughed out, drilled the 3 holes, finished the bottom, intermediate, and top steps. Now let's do a little bit of chamfering here, here, and here. The chamfering processes, along with the chamfering tool, are already in the process demo process folder. Bottom deburr has the final depth for the bottom deburr. When we import it, up comes the tool, up comes the process with the right dimensions. All we have to do is drag the profiler down into the bottom of the part where it will highlight the geometry. We click on the geometry and create the first deburring process. It's time for the second deburring process, which has a different height and a different width. We save that one as well. Let's go back into the folder. We have bottom deburr. We also have top deburr. Once we import top deburr, it will populate the process list, and we can drag the profiler up into the bosses, select the two bosses with our control key, and click Do It. This part has now been completely machined except for the bolt holes. Let's have a quick look at the machining operations. Face mill, volume mill rough. The first step. Volume mill rough, the intermediate step, and the top step. The drilling and the chamfering are now complete. In the next phase of this part, we will leave OpSim and work on the bolt pattern at the top of this part. Let's take a look at what the hole manager did with this part. We'll turn off the profiler for now, and let's zoom in on the holes and see what happens. When we right-click one of the data sticks and select Edit Hole, it tells us everything that we need to know about that hole, from the top chamfer to the counterbore to the through hole. Every hole in GibbsCAM gets hole data assigned to it in 3, 4, and 5 axis. So the hole manager can be used for automated drilling of 3, 4, and 5 axis parts. Let's grab the 3/8 spot drill, go to Holes, Feed In, Wrap It Out, and on Hole Feature, R level is from Hole Feature. At Op End, same as R level. Top surface Z, top of hole. Feature depth Z is going to be chamfer, and yes, adjust for tool tip. We will click the holes, right click just the one, select hole group, and group 7. When we click Do It, you'll see that the holes are quite a bit out of order. Let's go to Modify, Sort, closest hole next, Do It, and Redo, and this bolt pattern is now shaped up. We're going to add one more tool. That's the drill. Hole feature. Instead of chamfer, we will select bottom of hole and minus 0.025, bottom adjust, and do it. We just drilled all the way through the part. We'll do the counterbore milling now. Again, in the holes process, mill bore, helix bore, hole feature, bottom of hole, no. Segment end, yes. Which segment? The 250-inch drill segment. We'll use bore diameter where available. 20 thousandths Z pitch, start at center, finish at center, cut a radius comp on, and done. This drilling was carried out almost completely automatic. At any time during the GibbsCAM process, you can reorder your tools or reorder your operations. Let's say that this is not tool number 1, it's tool 12. Simply drag it and drop it down into the tool list until you find slot 12 and drop it. Over here on the operation side, the operation list automatically updates with the new tool position. You may also drag and drop operations. Let's move these two drilling ops to the end of the program. Again, you can change your mind very quickly inside of GibbsCAM. Now that the 3-axis work has been completed, let's switch over to another part file and look at 4-axis position milling. In 4-axis position milling, we aligned the part exactly like we did in 3-axis, except we now have the part on its side. Here we will grab the 3/8 spot drill, and you will see how simple it is to program a part in GibbsCAM in 4-axis. Here it's a drilling cycle, feed in, wrap it out. Hole feature, we will set feature depth Z to chamfer, and yes, adjust for tool tip. There's something new here. Machining coordinate system will be from each hole feature. That way we do not have to create a coordinate system for each hole. GibbsCAM does it for us automatically. We simply select the holes in the order that we want them drilled and click Do It. Let's take a quick look at this toolpath before we build another. Here we are on the 4th axis platter. And let's watch this toolpath run. Drill, 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 drill. Now, let's create the other 2 operations on the outside of this part. One will be a drilling operation. The other will be a helix mill bore operation. Let's grab the tool for the through hole, set our PEX cycle to chip break, and on hole feature, we'll only change bottom of hole and add a little bit of extra depth to the hole by adding a minus 0.025. We don't want any surprises and any material left in the bottom of the hole. We click Do It, and we now have our drilling operation automatically around the 4th axis. The last operation here in 4-axis position milling is a milling operation with this 3/16 end mill. It will be a mill bore, helix bore. The hole feature, we will change bottom of hole to segment end. And the end of the segment is the end of the 250 bore with no bottom hole adjust. Let's check our bore parameters. Use circle diameter available will cause the end mill to cut the right diameter. The Z pitch will set the Z pitch per revolution as it moves down in the Z axis. Start at center, finish at center, cutter radius compensation on, and do it. We now have all of the tool paths for this 4-axis positioning part. Let's slow the replay down just a little bit and go. Spot drill, PEX drill, and helix bore. At all times during simulation where you have the holder and the fixture and the part shown, GibbsCAM is checking for collisions and will alert you right away so that you do not send your mistakes down to the floor. Now that we have completed the part in 4-axis positioning, let's start to examine what GibbsCAM does with 3-axis, 4-axis, and 5-axis surfacing. Now that we've had a look at 4-axis position milling, let's open another part file and see what 3D SolidSurfacer is all about. In GibbsCAM, SolidSurfacer is used when you have an irregular surface that cannot be cut with a flat end mill and must be cut with a ball or other type circular cutter. We have several different 3D SolidSurfacer strategies laid out for you, and let's explore them to see what we have. Surface flow cut is perfect for a number of different types of surfaces, and in particular this one, a circular surface. There are multiple strategies inside of SolidSurfacer: lace cut, two-curve flow, surface flow cut, intersections, edges, faces, auto. In this particular toolpath, we will apply surface flow cut to this part with a step over set by us, either with step over or with ridge height. You can select either one of these and the other will be driven by it. Finish, spiral, cut along long edge. And all we have to do is click the surface and press the Do It button, and we have our spiral toolpath. Let's have a look at this spiral toolpath, just this first one. Rewind and play. Here we go, SolidSurfacer with surface flow cut. We also did a surface flow cut in operation number 2 on the other side of the part. So let's skip to operation number 3 and talk about lace cutting. Lace cutting, look down at your shoes and see how they are laced. In lace cutting, we have a number of different strategies that we can use to cut the part. Under options, we will select one finish pass on all surfaces. And on toolpath, we are using line segments. The surface will start above the part and cut below the part by half the radius of the cutter. Since that's 3/32, I went to minus 0.1. And this is a back and forth strategy. Let's have a look at this lace cut on this part. And here we go. There is our lace cut, and it does skip over the center parts of the cavity. Moving on to the advanced SolidSurfacer, there are more features available to us in the lace cut category, such as raster, radial, or spiral shape toolpaths, and on the Options tab, we can add fillets to soften the machine movement between lace cut stepovers. We also have control over the entries and exits on this part by selecting entry and exit styles of axial, vertical, horizontal, or both. And the boundaries can be of different strategies as well. We're going to use a silhouette boundary, which is the shape of the part. And stock type is solid, and that is the solid that we have in the body bag. Let's have a look at this toolpath in Advanced SolidSurfacer. On this particular toolpath, you'll see that it completely avoids the cavity in the middle of this part, and we have these nice swoopy lead ends to make entry and exit much smoother on this particular part. This was the Advanced SolidSurfacer Lace Cut. The next strategy that we'll explore in the Advanced SolidSurfacer is Constant Step-Over Cut. It's very similar to Surface Flow Cut. In the Advanced 3D SolidSurfacer, we have many more different types of cutting strategies. In this case, we're going to select the surface and a simple constant step over. Again, we can use either the step over or the scallop height to develop this toolpath. Now this toolpath, we're going to step it up a little bit in operation number 6 by using another strategy called curve projection, and it gives us an even more simple toolpath. Curve projection, we get to draw a curve and then select the surface, and when you select the surface and the projection curve, this projection curve will guide the tool around the surface. If we made this projection curve square, it would put a square toolpath around the surface. And again, under Options, we have fillets if we need them for spiral, entry exits, the same, and of course our boundary is silhouette, and stock type in this case is none. Let's go to OpSim and watch operation number 6. Look at the beautiful swoopy lead ends that do not leave a witness mark on the part when we are cutting with this 3D strategy. And as you can see, we can start on the inside and work out, or we can work on the outside and work in. Here we have our circular strategy. Let's rewind that and slow it down just a little bit. Let it rewind, pull the throttle down, and let's see what we get with a little bit slower. There we go. This is a circular toolpath in Advanced 3D SolidSurfacer using a drive curve that is driven by you. You can shape your toolpath by selecting and drawing your own projection curve. Moving on to the highest level of GibbsCAM milling, let's have a look at 5-axis positioning and 5-axis simultaneous milling. With a 5-axis milling machine selected, we simply set it up like we did any other file. And here, as we did before in the previous exercises on the 4-axis machine, 4-axis and 5-axis positioning is very, very simple with the addition of the hole manager and automatic feature recognition. Automatic feature recognition automatically creates the proper coordinate systems for 4 and 5-axis position milling. We simply click the features as normal, press do it, and we have our tool paths. We have our drilling tool paths and our milling tool paths. Now let's have a look at the 5-axis module and look at some simultaneous milling. Here we have 2 curved surfaces on the top of the part that we machined earlier in this demo on a 3-axis machine. On the 5-axis machine, we will use the multi-axis package, which gives us tremendous power in programming these complex machines, and also expands your repertoire to many different types of toolpaths. including cavity tilt curves, cylinder head machining, electrode machining, impeller and turbo machinery. In this exercise, we are going to machine the top of this part using both 4-axis and 5-axis simultaneous. Each of these tabs must be mastered in the multi-axis package, but will bring you great strength in your programming for your shop. Here we will select surfaces and parallel to curve. We select our edge curve to cut parallel to. We select our drive surface, which is the top of the part. Here we set drive surface's clearance, which is how much stock. We want a spiral tool path with a ridge height of 1/10,000th of an inch. In this case, tool axis control will be 5-axis with a tilt angle of 8 degrees because the end mill doesn't do any work at the center of the cutter. No matter how many million RPM you spin a ball end mill, the center of the ball end mill is still moving at 0 surface feet per minute. So we will use a first sweet spot angle of 8 degrees side tilt. No gouge check is required. In link, we will set our approaches, and that's it. And when we click do it, we have a tool path very quickly in 5-axis simultaneous. We can also do 4-axis simultaneous in exactly the same way. The same parameters are checked here on the Surface Paths tab, but under Tool Axis Control, we will choke it down to 4-axis with a tilt angle of 8 degrees. When you see this run, you will understand the difference between 4 and 5-axis. Here, let's have a look at OpSim and watch the tools cut the part. Tools cutting around the outside of the part, and this is very nice, and it does show us quite a bit about the part, but let's expand this demonstration one notch higher by going to Machine Simulation. Easy programming of 5-axis machines includes the GibbsCAM 5-axis and 4-axis and 3-axis machine simulation. Here in Machine Simulation, you get to see the whole machine and all of its axes working at the same time. Collision checking is always on and is looking for collisions between the machine, the fixtures, the components, the holders, and the parts. In 5-axis, you get a real picture of what is going on inside your machine with Machine Sim. Without Machine Sim on a 5-axis machine, you're just guessing at what is going on inside. As soon as we get to operation number 13, you will see the difference between 5-axis surfacing and 4-axis surfacing. Here in 5-axis, there is quite a bit of rotary movement while we're cutting this part. And if we want to switch to 4-axis and see a different type of movement, let's let this toolpath develop a little bit further while zooming in. And we can see the 5-axis machine maintaining the 8-degree tilt angle so that the cutter is actually doing some work. That's a lot of movement. Let's choke it down to 4-axis in the next operation. In this operation, we will set our tool axis control to 4-axis. In Machine Sim, we will go back and we will skip ops 1 through 13 by clicking the Skip Unselected Ops button. And at the same time, it will generate the material condition for operation number 14, and all we have to do is push the Go button. Now we can see that we have choked the machine down to 4-axis simultaneous. There is much less movement inside the machine, and we still get our 8-degree tilt angle. In 5-axis and 4-axis CNC machining, there are new items that are inside of your controls, such as tool center point control programming, dynamic work offsets, and other unique features for your 4 and 5-axis machines. Here in the code, you'll see right at the top of the program G254 and G255, which is dynamic work offsets. Here in the 5-axis toolpath on operation number 13, you can see we have dynamic work offsets and G234, which is tool center point control programming. GibbsCAM supports all of these advanced features inside of your 5-axis controls. We hope that you enjoyed this thorough GibbsCAM demonstration, and if you saw something you like, or if you would like further information, please contact your local GibbsCAM reseller.